there are a couple of misconceptions that many people carry regarding a few things about a diode. It's a simple element, but there are quite a few misconceptions that are there. One of them is, one of the misconceptions associated with the diode, PN junction diode, is what is the typical value of reverse saturation current? Right, so for most, this is a sort of not an easy question, because typical, when something varies a lot over several orders of magnitude, saying something typical is difficult, right? But nevertheless, when this question is often posed, so what we are talking about is this equation I naught equal to Is e to the power Vd by nVt minus 1. So often when we ask these questions to students, a typical answer that we get, and if you talk to people, a typical answer that you get is, what is the value of typical value of Is? People say microamperes. In microamperes, you would find it in books as well, and you go and check out at many resources, many places, you would find Is is in microamperes. Now, is that a good value? Is in microamperes. And obviously, when we ask what is the typical value of Vd, that also 0.7 volt, right? One of the most common values of diode voltage that we offer is 0.7 volt. And for Is, we say in microamperes. Obviously, a very quick calculation will show you that these are inconsistent. Just putting these numbers, for example, if Is, let's say I take 10 microamperes, ideality factor n equal to 1, and I put these numbers here. For V naught equal to 0.7, we get 5 million amperes. 5 into 10 to the power 6 amperes, right? No diode would sustain a million ampere current, so obviously it's a ridiculous value. So the two, if you say Is is in microamperes, ideality factor you take equal to 1, and you say diode voltage is also around 0.7, these are mutually inconsistent values. The other way of showing it is, well, let's say if you're doing a circuit like this, you're making it in the lab, and you assume 0.7, you would get 1 milliampere, right? 0.7, 1 milliampere. So I can take these numbers here, 10 microamperes and n equal to 1. I can put it in this equation, the upper equation, and I ask myself, what is the diode voltage required to get a current of 1 milliamperes? Well, for ID equal to 1 milliamperes, if I put in these values, Vd equal to 0.12 volts. So that's also ridiculous. We don't find that the voltage across the diode to be 0.12. That's too low. Just as Vd equal to 0.7 is implying 5 million amperes is obviously wrong. Similarly, ID equal to 1 milliampere implying Vd equal to 0.12 is obviously wrong. So when people say, well, the reverse saturation current is in microamperes, diode voltage is 0.7, these are not right. I mean, they are by any any diode that I take, these are not the right values because of the obvious numbers that you're seeing, 5 million amperes and Vd equal to 0.12. So if I'll come to the question, what is a typical value is hard to answer, but now you're doing the experiment in the lab, you're measuring the diode's characteristics, and part of that is to measure Is and N. And if you do that, by the way, this Is, as I said, even for the same diode with the number 1N4007 mentioned, these values will vary. Okay, so there's considerable variation. These are the diode's characteristics measured using what we have is a fairly precise measuring instrument, not the one that we use in the lab, a much more precise. So you can see we can easily measure using that instrument currents below picoamperes also. So in this case, when we measure the diode's characteristics, you can compare with these numbers. What we find is a saturation current of 5.9 into 10 power minus 10, about half a nanoampere. Oh, sorry, 0.6 nanoamperes. Okay, and ideality factor of 1.5. It's not common that you will pick a diode in the lab and you'll find that its ideality factor n is close to 1. You will not find that. You'll find ideality factors of 1.5, 1.6. You could find 1.2, but finding an ideality factor of n equal to 1 would be sort of rare. So, a more accurate, a typical value to keep in your mind. So when somebody asks you what is the typical value of IS, so instead of saying 10 microamperes or microamperes, a better number is, let's say, based on the measurements that you would do it, a better number is by saying that IS is equal to 1 nanoampere, n equal to 1.5. So IS is of the order of a nanoamperes, ideality factor is 1.5. These would give you, for 1 milliamperes, VD would be 0.55. It won't be 0.7, even for these numbers. And for VD equal to 0.7, ID would be equal to 68 milliamperes here. So if you want to quote a typical value, don't say 10 microamperes and ideality factor of 1. This is a better value here, okay? 1 nanoamperes, ideality factor of 1.5. You can see here, obviously much better than a typical value that many people quote is in microamperes and ideality factor of 2. So that's totally or obviously wrong here, okay? So that's the first point. If you are asked to give a value for IS, keep in mind, I'll just show you in a minute, the value of IS varies a lot. But if you are asked to give a value of IS, give a value of IS which is more realistic, 1 nanoamperes, and couple it with the ideality factor of 1.5. 1.5 makes a lot of difference here. It's an exponential function. If you put 1 here, n equal to 1, it would make a lot of difference to what voltages and currents you get here. So ideality factor of 1.5, IS of 1 nanoamperes here. Okay, with that in mind, let me show you another diode. One is a diode that you are measuring in the lab. If you take a bipolar transistor, you'll also be measuring bipolar's characteristics here. Note that base emitter junction is also a diode, right? Base emitter junction is also a diode, and any diode can be modeled by a function just to denote that is associated with base current. We call it IBS, exponent VB, and VT here again, right? So what is the saturation current here? And what is the ideality factor here? All right, so we have not asked you to measure this. You could try. So again, the characteristics are shown. This is the base current plotted against base emitter voltage. And what we have done is we've kept the collector at 5 volts. So that keeps the collector base junction reverse bias, so that our measurements are not affected by collector base junction is reverse bias here. Okay, so this is the characteristics that we get. And the plot here is not, you see, it's a log versus linear. So it's not a very good straight line, which means it doesn't follow a simple exponential equation all throughout. So I've taken the data here, this particular part here, which is close to 0.6 or so, 0.6, 0.7, around that particular point here. We can fit a line here. We can fit a straight line here, fit this particular equation. And the value that we'll get is, what will be the saturation current? Any guesses? What is the likely saturation current? Any wild guess anybody wants to take? All right. Look at the value. 1.3 femtoamperes is for the transistor. It's not some fancy, very small transistor. It's the transistor that you will use in the lab, right? It's the base, the diode that is there in the base emitter junction. Look at the value of IS. 1.3 into 10 power minus 15. Okay, femtoamperes. That's why I was telling you that giving typical values are so hard. When for the diode that you're measuring in the lab, the saturation current is a nanoampere. For the same bipolar transistor, if you measure the base emitter diode, the saturation current is 10 power minus 15 amperes. Ideality factor is 1.14. Now, this is here in this part of the characteristics, right? If I were to fit in another part of the characteristics, all right, so the values that we get here, if you apply base emitter voltage of 0.7, the base current that you get is around 40 microamperes here. Okay. If I were to fit a straight line here at some other part of the characteristics, I get IBS of 70 femtoamperes, N is equal to 1.46. So what I'm trying to tell you is ideality factors are also not constant in general. You may have one ideality factor at some lower bias, another ideality factor at some higher bias. These ideality factors also change. So it's not that every diode can be described by one single equation like this here over these entire characteristics. You'll have to use different values of IBS and different values of N depending on which region you're operating in. If you're in this region, you have one value. If you're at some lower region, you have some other value. So again, so what is the typical value of saturation current? Well, if something can vary from a nanoamperes to a femtoamperes, well, you can't really say what is typical, right? I mean, there is no such number like that. What is the typical value? But what I was trying to emphasize is that if somebody says a 10 microamperes and ideality factor of 1, that gives you wrong values. That gives you all wrong set of, it starts predicting 1,000,000 amperes and very, very low diode voltage. So that's not a realistic number. If you have to quote numbers, you could quote numbers like this. Like in a bipolar transistor, base emitter junction diode is given by these particular numbers here. Anyway, so these are, we have not, as I said, we have not asked you to calculate, but if you wish, if you have time remaining, you can take your bipolar transistor, measure the diode that is there. You can try and measure its characteristics also and see how that behaves. The other thing is you must be wondering, is there any diode whose ideality factor N is equal to 1? Do we see N equal to 1 at all? Well, not exactly a diode, but if you take your bipolar transistor again, and again is biased in the forward active mode with 5 volts here and base voltage is varied. If you look at the collector current, instead of looking at the base current, the collector current also follows this exponential equation. And if I look at this, this is the collector current. And you see here, except at higher biases where I'll come to later on, you see that it's a very, very good straight line. It's a very good straight line, which means the collector current dependence on base emitter voltages is an exponential over 7, 8, 9 orders of magnitude. It's a very good exponential. And the ideality factor that we measure for this is very close to 1. In fact, it is, from theory, we can say it is equal to 1. And in fact, so if you, what you can do that is you can use it to measure temperature. So in this case, note that the reason why I've written approximately equal to 1, I didn't know what was the temperature in the lab and of the device when this characteristics was measured. So I didn't have exact value of VT. And if you don't have exact value of VT, and if you measure the slope here, then you can't calculate N. In fact, from theory, we know N is very, very close. And measurements have also shown where you know the temperature exactly, that N is close to 1. So this is a very good way of actually measuring temperature. All that you need to do is measure your, which we will do in 381. When you come to 381, we'll use a transistor and use this dependence on temperature here to actually measure and build a sort of a thermometer here. All right, so that's as far as what is the typical value of IS. Okay, so if you're confronted with that question, what is the typical value of IS? Well, 1N4007 has a nanoamperes ideality factor of 1.5. On the other hand, a bipolar transistor may have in femtoamperes, again, ideality factor of, depending on where you do it, could be 1.5, could be 1.2. Okay? The other question, is reverse saturation current really the reverse saturation current? This is also something that you can explore in the lab. Is it really the reverse saturation current? So what do I mean by that? Well, this is the equation that we are using. And from this equation, if I put, so this equation we are using in forward bias. Remember, we are measuring the characteristics in forward bias and fitting this equation. But if I use this equation, as we all do, implies that for reverse bias, if I put V equal to some -1 or so, I would get ID equal to -IS. And that's the origin of the name for this particular IS as reverse saturation current. That if I put in a reverse voltage, V is minus, I will get I equal to -IS. And obviously, ID would be independent of voltage. Whether you apply -1, -2, -3, or whatever, the value of ID is -IS. So this is also there. Is IS really the reverse saturation current? So again, the same diode that you are using in the lab. For this, I've already said the IS is 5.9 into 10 power minus 10 amperes. Okay, so 0.6 nanoamperes, N equal to 1.5. So if I take this particular diode and I reverse bias it, say apply a minus 1 volt to this particular diode here, I should expect 0.6 nanoamperes, right? Minus 0.6 nanoamperes. That's the reverse saturation current. But if you do that in the lab, it's a little hard to measure because the current is small. If you do that in the lab, see, it is in the reverse. See, I'm measuring from 0 and going towards minus 1. You can see the current is almost constant. The current is almost constant because the current is low, so there's a little bit of noise here. So what you find is 4 nanoamperes. So the actual reverse saturation current is how much? Well, in the reverse bias, the current has saturated. The current is almost saturated. What is this value? 4 nanoamperes. While this value IS that I extract from here is 0.6 nanoamperes here. All right. So what it says is 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 not the reverse saturation current. It is not reverse saturation current. If you're thinking that I'll take a diode, measure its IS and N, and with that I would be able to tell what is the reverse current, that's wrong. In fact, it's not just, you can see here it's off by a factor of, you take 4 here and 0.6 here. So it's off by almost a factor of 8 or so. And in some cases it can be off by a much larger factor also. So IS is not the reverse saturation current. Although the name is there, reverse saturation current. In some cases, in some diodes, maybe it may turn out to be that in the reverse bias, the current that you measure is also equal to IS. That may turn out to be. But in general, IS is not the reverse saturation current. If you want the reverse saturation current, if you want this current here, you have to actually go and measure it. You have to apply minus 1 volt, minus 2 volt, measure the current and see what it is. You can't get it from this equation. In this equation, IS is simply a sort of a fitting variable, which is obvious as I showed you for a transistor. As I showed you, if you take this part of the characteristics, I said IS is 1.3 femtoamperes. If I take some other part of the characteristics, IS is 70 femtoamperes. So obviously, IS is not the reverse saturation current. It's just what you are doing is you are applying this particular equation to the forward bias characteristics, and depending on different regions, you may get different values of IBS that is there here. Okay, so do not confuse this with the reverse saturation current. If you really want it, you have to go and measure it. Okay, so that's the other point that was there here. This is simply a current that you use to fit the forward characteristics. That's all. Okay, so that's the other part here. Third part, how large can the PN junction voltage be? The number that you carry in your heads are 0.6, 0.7. Can it be 0.8? Can it be 0.9? We're talking about silicon PN junction diodes. Can it be 1 volt? Can it be as large as that? Okay, so let me show you again. This is the measured diodes characteristics. See the plot? The same 1N4007. Nice exponential. And then this exponential starts to, the current, as you go to higher and higher biases, the current starts to saturate here. So what is happening is that the current is nicely exponential up to a point, and as you increase, note that it begins to depart, in this case, even at 0.7. 0.7 is over here, is no longer a pure exponential. It's departing from that. The voltage at this point is 1 volt. So your diode can sustain 1 volt, can sustain 1.1 volt. Okay? But what is happening is the characteristics are no longer exponential. As you go to higher and higher biases here, they depart from the exponential nature that you expect here. If you go into this region here, so here is nicely exponential, here it is not. So if you go in this region here, let's say if I focus on this region here, which region? Let's say from 0.9 to 1 volt. So I'm looking at higher biases, 0.9 to 1 volt, and if I plot the characteristics, look at the nature of the graph, 0.9 to 1 volt. The nature of the graph is linear. The diode is not exponential anymore, it's linear. In fact, we can fit this particular line here and extract a resistance of 3.5 ohms. This is for the diode that you are handling in the lab. So if you do go to higher biases, your diode is no longer an exponential characteristics, becomes more linear. So there are resistances, contact resistances, other resistances that are there inside your diode, which become more important. So even the 3.5 ohm resistor, it begins to dominate the characteristics when you go from 0.9 to 1 volt. And because the characteristics of the diode is more like the exponential characteristics that you know of. In addition to that, there is a series resistance of, for example, in this case, about 3.5 ohms here. But to estimate that, you'll have to go to higher currents, 50, 60, 70, 80, that kind of a current here. And those kinds of currents are difficult to measure in the lab. Op-amps have a limitation of 20 milliamperes or so. So we have not asked you to measure this, but if you were to do it, you'll find that the characteristics are linear and 3.5. And it's for that reason that we don't go, you normally find that we don't go and operate the diode at 0.9 or 0.95 or 1 volt. It's no longer exponential. It's no longer exponential, it's linear. It's linear here. And linear means that if you double the current, the diode voltage would also double. You don't want that from a diode. In the normal applications that we use, we want the diode voltage and forward bias to be as small as possible. That leads to power dissipation and all kinds of other issues that are there. So we would like to keep diode voltage small, and therefore we would like to operate in the exponential region here. And for that reason, we restrict ourselves to 0.7, under 0.7 or 0.75 or so. But you clearly see that you can operate at 0.9, you can operate at 1, you can operate at 1.2, but the voltages are larger. The diode is more like a resistance.